Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at how to create a simplified version of conservation of mass equation using the Reynolds Transport Theorem that we have learned in the previous video. Now the equation for conservation of mass is called continuity equation, and this equation is very important in order for you to know the mass flow rate getting into and exit of a control volume. Previously we have looked at what is the definition for conservation of mass in terms of system, and then we have seen the equation which is called the Reynolds Transport Theorem in order to convert that system into control volume. And now we want to take that equation and simplify it even further so we can use it to solve engineering problems. Now let's take a look at what is our original equation for Reynolds Transport Theorem, and it looks something like this. This is your original Reynolds Transport Theorem, and I'm gonna write it again here, and this is dn system over dt, and remember that n system could be mass, momentum and energy, equal to integration of control volume, this is d over dt eta rho times dv, plus integration of control surface, this is eta rho normal dot v times dA. So this is our original equation for Reynolds Transport Theorem. And the definition for conservation of mass is that the mass inside the control system is fixed. It doesn't change, okay? So this is dm inside the system over dt must equal to 0. And mass inside of a system is actually d over dt. This is integration inside the system, rho dv, and this is equal to 0. And remember, this is volume. And for eta, when the end of the system is mass, eta becomes 1. And we have looked at this before in this equation. Okay, so what happens to this equation when eta is now 1, right? So we know that now dn system over dt is equal to 0 because of the conservation of mass definition, and this is equal to cv d over dt. Remember, eta is now equal to 1, so now what you have here is rho times dv plus integration of control surface. Again, eta is 1, so this is rho normal dot velocity dA. And now we have managed to get rid of theta inside this equation. And what do we do next? If the flow is steady, if flow is steady, meaning that inside the system, the flow does not change with time. It means that if you have d over dt, this term is definitely 0. And inside this equation, you have this d over dt here. So this becomes 0 because the system is steady. If the system is not steady, then you cannot cancel out this term. But now let's keep assuming that the flow is steady. So when that term becomes 0, so now 0 becomes integration of control surface rho n dot v dA. Now this is quite simplified already, but of course we can simplify it even further. Now this is control surface, and control surface is the surface that defines your boundary of the control volume. And if you have a control surface that looks something like this, okay, and the flow comes from left to right, and this is your control surface. So your control surface has one inlet and one exit at point 1 and point 2. And remember that the normal direction has to always be going outward of the control volume. Okay, so your n goes this direction. This is n at 1, and your n is going to this direction. This is your normal at point 2. So normal at point 1 will be negative. Alright, so when you have only one inlet and one exit, what you can do with this equation is actually rho 1 v1a1, but now n1 dot v1, because v is going from left to right, but n is going from right to left. So what happens is this will be negative, and then plus rho 2 V2 A2. Now V2 is positive because V is also going to the right, okay, and N is also going to the right, so it becomes positive, and this is equal to 0, and you will end up with rho 1 V1 A1 equal to rho 2 V2 A2. And if the flow is incompressible, meaning that the density at point 1 is equal to the density at point 2, so you can simply cancel out rho 1 and rho 2. And this equation becomes V1A1 equal to V2A2. And these two equations are very simplified, but it's also very important. You're gonna certainly use it in every problem that you're gonna work on after this, okay? And this equation is called continuity equation. And mass flow rate, or m dot, is defined using rho times velocity times area, and volume flow rate, and we call it Q, is defined using velocity times area. Okay, and the conservation of mass says that m dot 1 must equal to m dot 2 and Q1 must equal to Q2. And this only applies when the flow is steady. And again, these two definitions are very important. So my suggestion is for you to remember it because you are going to be using this again and again. Okay, now that we have found the equation for conservation of mass, let's do a few examples so you can understand it better how to use these equations. Okay, so the first example is a very simple one. So this is an example. And you have here a converging pipe. And the larger pipe has a diameter of 100 millimeter. And the smaller pipe has the diameter of 20 millimeter. And it's also given that the velocity is moving from left to right, and the inlet velocity here is 3 meters per second. And now the question asks you to find what is the V2, which is the exit velocity, and also what is the flow rate, which is Q. Okay, so in order to solve this equation, so first of all, let's draw our control volume. Right, so let's say our control volume looks something like this. And this will be our point 1 and this will be our point 2. Okay, and we know from these equations that rho 1 V1 A1 equal to rho 2 V2 A2, and also if density is the same, which is the incompressible flow, V1 A1 equal to V2 A2. Alright, so now let's assume that this is incompressible flow, so it's simply V1 A1 equal to V2 A2. Now you are looking for V2. This looks quite simple already, so this will be V1 A1 over A2. So V1 is 3 meters per second, A1 is pi D1 square over 4, and divide by A2, so this will be times 4 pi D2 square, right? So we can cancel out 4 and also pi. So this will be 3 times D1 over D2 square, and this will be 3 times, and D1 is 100 millimeter, so this is 100 millimeter, so 0.1 over D2 is 20 millimeter, 0.02, and this is square, and V2 will equal to 0.1 divided by 0.02 square times 3, that will be 75 meter per second. Okay, now let's see if this answer makes sense, right? So 75 meter per second, and we know that V1 A1 equal to V2 A2. So when A2 is less than A1, this means that V2 will be higher than V1. Okay, so I think this makes sense because now we have V2, which is equal to 75 meter per second, which is definitely higher than 3 meter per second. So V2 is completed, and now let's find out what is Q. And Q is simply velocity times area, and Q1 is equal to Q2. Q2 cannot be different than Q1 if the flow is steady, right? So it doesn't matter when you have here Q equal to velocity times area. So it doesn't matter whether you take velocity and area at point 1 or velocity and area at point 2, because it's always the same. Okay, this is V2A2. Now let's find using point 1. So velocity at 1 is 3 meter per second and diameter is 100 millimeter. So this is 3 meter per second, pi times 100 is 0.1 meter square over 4, and your Q will be pi times 0.1 square divided by 4 times 3. That will be 0.0236. This is 0.0236. And Q is in meter cube per second. Alright, I think I forgot to mention this before. So the unit for Q is meter cube per second. And the unit for mass flow rate, this is of course kilogram per second. Alright, and now we know that Q for this problem is 0.0236 meter cube per second. Okay, this is a fairly easy example just to get you familiar with the equation of mass flow rate and also volume flow rate. Now, for the second example, let's take a look at what happens if the flow is not steady. Okay, let's take a look at it now. So, example number 2. This is example 2. And what you have here is a device of some sort. Okay, you don't know yet what is the device. And this device has one inlet and two outlets. And the condition that is given at each inlet and outlet is, this is at inlet is given to you that V1 equal to 10 meter per second. And this is your exit, and it's given that m dot at point 2 equal to 4 kilogram per second. And this is another exit, but this time it's given that Q3, remember Q is our volume flow rate, and volume flow rate is velocity times area, and this is equal to 0.008 meter cube per second. And the medium is water. And the question asks you to find the rate of change of mass of the water. This is dm over dt inside this device. So what is the dm over dt inside this device? What is dm over dt? dm over dt is the rate of change of water inside this device. So immediately you know that this is unsteady problem, which means that whatever comes into the control volume is not necessarily similar to what comes out of the control volume, because something has changed inside that control volume, right? Now let's take a look at what happens. But first of all, of course, we need our control volume. So let's draw here, and let's say our control volume looks something like that. As long as it covers inlet and exit, that will be fine. And this will be your point 1, this will be your point 2, and this will be your point 3. Now let's check out our equation for Reynolds Transport Theorem, because if you remember, when we arrive here, that rho 1 V1 A1 equal to rho 2 V2 A2, we already assume that the flow is steady. But our problem now, the flow is not steady, so we can no longer use this equation. So we need to go further. Okay, remember that this is when we cancel out this term, alright? But now let's uncancel that and see what happens to the equation. Alright, so when we uncancel that, what happens is we have this. Let me copy this equation first. And I'm going to put it here. And see how we can solve it. And we know that here, this equation is quite simple. This is simply rho times velocity times area. If it's the inlet, then it must be negative. And if it's exit, then it must be positive. Okay, let's deal with that first. And we know that at the control surface, we have one inlet and two exit. So at point 1, okay, so this is minus rho 1 V1 A1. Remember that we are solving for this only. Okay, so plus rho 2 V2 A2 plus rho 3 V3 A3. Okay, why is that positive and why is this negative? Because we understand earlier that when the flow is going into the control volume, the normal will be opposite direction with the velocity, so that gives you negative sign. And when the flow exits the control volume, the normal of the surface and the velocity is on the same direction, so that gives you positive sign. Now we know that 2 and 3 is exit, so positive and positive, and we know at 1 is inlet, so this is negative. Okay, so now this part is done. And what happens to this one? We know that rho times dV is mass. Okay, and the reason why we need to integrate this is if the rho changes with volume. But now, because the medium is water, right, we know that the density will not change. Okay, so this term can be simplified as dm over dt. And this will equal to 0. Now suddenly this equation looks more sensible to us because this is what we are looking for in this question. We are looking for the rate of change of the mass of water, right? So now let's see how we can solve this. So dm over dt will equal to rho 1 v1 a1 minus rho 2 v2 a2 minus rho 3 v3 a3. Okay, change the sign because now I'm moving this to the left hand side. Right, so what is rho 1 v1 a1? It's only given that velocity here is 10 meter per second. Okay, so rho 1 is 1000. This is water. V1 is 10 meter per second, and now we need the area. I think I forgot to tell you that the diameter here would be 8 centimeter. Okay, so this is simply 0.08 square times pi over 4. Alright, so this is rho 1 v1 a1, and what is rho 2 v2 a2? And looking back at this question, it's given to you that m dot is equal to 4 kilogram per second, and m dot is already rho times velocity times area. So rho 2 times v2 times a2 is simply m dot 2, which is 4 kilogram per second, and minus rho 3 v3 a3. Let's take a look at 3, and here 3 is given as q, and q is simply velocity times area. So v3 times a3 is 0.008. So what you need now is just the density, which is 1000, and v3 times a3 is 0.008. And let's see if we can solve this. So this is 0.08 square times pi divided by 4 times 10,000 minus 4 minus, this will be 8. So that will be 38.27. And the unit, what is the unit? The unit will be kilogram per second. So now we have found the change of the flow rate of the water, which happens to be 38.27 kilogram per second. So if you imagine this problem again, okay, so the device that is in here always accumulate mass of water at the rate of 38.27 kilogram every second. So every second pass by, there's 38 more kilogram of water that is going into the device. So you know that this device is accumulating water. Why is it accumulating and it's not discharging water? Because this is positive, right? So you know that the water will always increase inside this device. So this device could very well be sponge. Okay, so this has to be a very big sponge because it accumulates water at 38 kilo per second. Or this could be something like a reservoir of water, or maybe a water tank. Okay, so this is if you have to take a guess. What is this device, right? You know that this device is accumulating water, so it could be a sponge, it could be a water tank, it could be a water bucket, and it could be anything. But the point is, now you know how to use the equation, not only when the flow is steady, but also when the flow is unsteady. Okay everyone, I think that's all from me for this video. Now that you know what is the volume flow rate and what is the mass flow rate. And you know that these two equations is called continuity equation, and these equations comes from the conservation of mass. So as usual, do this example and this derivation again and again until you are familiar with how this equation works. Remember that continuity equation is a very important equation and you would almost certainly use it in any engineering problem that you are going to work on after this. Thank you very much and I'll see you soon in the next video. Bye!